This is like a cut of a real lens. And what this does on top of a pinhole, it collects the light. So there's still just a single ray of light hitting a pixel, while initially there are multiple rays of lights collected to a single one. However, the issue with this, it makes our camera model more complex and things generally become more complex. And what does this complexity mean? Basically, this is what causes our lens distortions in the image, which we tried to get rid of in the first image of this slide deck. So let's add this thing mathematically to our camera model. And first of all, what are lens distortion in more detail? Here you see an image which seems heavily distorted, but actually this is an image with no optical distortions. What you see here are purely perspective distortions. This is like photography, or aesthetically this is maybe also not desirable, but if we want to do computer vision, this is what we actually want, because in this space everything is linear, the lines are straight, and we can compute things and distances. As you can see, this is blurry at the edges. This is because this is an undistorted image. The distorted counterpart to this image is this. And the distortion you see in this image is radial distortion, like heavy radial distortion, because this is captured with the fisheye lens. The fisheye lens has a special property where the angles between things are reproduced correctly. So the right angle here is still right, but the lengths are not correct, and also straights are not straight, which you can easily see also in the upper left corner of the image. So if we want to go from this image to this image, how do we model this mathematically? Well, the answer is this formula here, but before we start discussing this formula, let's take a look what it does. This is depicted in this image, a little bit simplified. So we see the effect of this radial distortion applied to a checkerboard pattern, and the checkerboard is distorted, and the yellow arrows here denote the distortion strength. So the end is the distortion coordinate, and the start of the arrow is where it should be if it's an undistorted image. So how do we model this? Well, we start with an undistorted point 2D point P and obtain a distorted point PD. And we do so by multiplying the point with this bracket. And why exactly this one? Well, actually we require surprisingly little about on the function which we model here, because this bracket here is just a Taylor expansion of some arbitrary function of radius. So r is like the distance from center of any point in here. And then the parameters of radial distortion are K1, K2 and K3, and they are just the coefficients of Taylor expansion of this unknown function. Furthermore, we only kept the even coefficients of Taylor expansions, like square to the power of 4 and to the power of 6. This is a rather arbitrary choice, but it's quite common when modeling radial distortion. My guess is that you do not have to consider the sign of the radius if you just keep the even exponents. And the image on the bottom was generated synthetically by setting K1 to 0.1 and K2 and K3 were kept to 0. So this is if K is positive, and if it's negative, then you get the inverse direction of the arrows, and it will resemble the fisheye distortion you've seen before. One thing to note here is that the function only depends on the radius. This means it's radially symmetric again around the origin, which is here. So while this radial distortion is probably the strongest distortion you see in images, typically one adds one more distortion, and we talk about it on this next slide. The next distortion is the tangential distortion. Again, you find the formula here, but we first talk about what it does intuitively. So what you see here is again the distortion of a checkerboard pattern, and yellow arrows indicate where things move. And if you look at the arrows, it resembles tilting the checkerboard pattern slightly back on the left side. And this is exactly the effect that this distortion tries to model, namely that the image plane and the lens is not properly aligned, that there's some angle between them. This typically happens if there's a bad build quality of the camera, then things are not really well aligned, and then you have this distortion. This distortion is modeled by the coefficients P1 and P2. X and Y are the 2D pixel coordinates of the point P, and we also have the radius in here. So this time this is not a Taylor approximation, but analytical derived tilting of the image plane. So now that we have talked about the two major distortions in conjunction with lenses, how do we put them together? We do it like this. So here we have our undistorted point P, and we apply the radial distortion, and then we add the tangential distortion on top. And the combination of the radial and the tangential distortion, we give this a name, which is the function delta, like distortion. So delta of an undistorted point P is its distorted position. So now that we have modeled the lens, we need to attach it to the pinhole camera we described before. And we do it like this. This part is the same like before, but we apply now it describes the mapping from a world point to the camera space, and also includes the Z division, and only now we apply the lens distortion. And then we continue with the K matrix, which we defined previously. So again, keep in mind that both the K matrix and lens distortion are applied post-projection. So the Z coordinate is cancelled out, and we are only talking about 2D points here. So this is now the full camera model we will use for the remains of the lecture, and let's talk now about how the full intrinsic parameter vector C looks like. It looks like this, and it contains the focal length in X and Y, then the principal point in X and Y. So this is these four parameters are the K matrix, or encoded in the K matrix, and then we have the delta distortion, lens distortion function, which has the three Ks from the radial distortion and the two Ps from the tangential distortion. So these 9 parameters are like the typical intrinsic parameters, which are used like everywhere. However, note this that there are only 2 kinds of distortion included, and there are also more distortions which one can consider. Like if the lens is tiltable itself, it's the tilt shift distortion. And if you talk about microscopes, then things also get more difficult, or at least different. So before continuing with how to actually measure these parameters, let's take a look how a real distortion field might look like. So what you see here is the distortion field. It's like lots of this yellow arrows, but drawn per pixel, and therefore we only look at their strength, which is encoded between blue, which is like 0 length, and red, which is maximal length. So this is normalized from 0 to 1. And the camera, which we calibrated here, is Logitech, this one, which is a typical and rather cheap webcam. And as you can see, we have the radial distortion, which is pretty prominent here. And it also has a slightly shifted principal point, because you see more of the radial distortion on this side than on this side. And if you look closely, you also see a little bit of tangential distortion in here. Like here, this spot is slightly brighter than this spot. So there's like also a small tilt of the sensor. And this is for a rather simple webcam, which comes quite close to the pinhole model, because things are simply that small. And it's also true like for cameras you have on a cheapish smartphone, like the more expensive one have multiple lenses with more complicated optics, but this is like a simple optic as you can get. And still we have radial and tangential distortion.